So we're just going to go through two quick examples for a hypothesis test of sample means for large samples. So our first question states a random sample of 50 medical school applicants at the university has a mean raw score of 31 with a standard deviation of 2.5. So what they're telling us here is that our sample mean was 31 and the standard deviation of our sampling distribution was 2.5. A student claims that the mean raw score for the school's application is more than 30. So at a 1% significance level, is there enough evidence to support that claim? So the first thing we need to do is we need to state our hypotheses and then define which one's going to be our claim. So the claim is stating that it's more than 30. So because there's no equality there, we know that that's got to be the alternate hypothesis. So our alternate hypothesis is that the mean is greater than 30. And I'm going to label that as the claim, just so we're clear. Which means by default, the alternate hypothesis and the null hypothesis are complements. So the null hypothesis, well, if you're not bigger than 30, that means you are 30 or less. So now that we have our hypotheses stated, we're going to first go calculate our test statistic, essentially, which is going to be our z-score. So our z-score in our hypothesis testing is where we take our sample average and we subtract it from the hypothesized mean, and we divide that by the standard deviation over the square root of the sample size. And here, since our population is big enough, we're approximating the population standard deviation with the sample standard deviation of our sampling distribution. So to calculate this, our average was 31, the hypothesis average is 30, and we'll divide that by 2.5 over the square root of our sample size, which is 50. And when we calculate that, we will get approximately 2.83. So now that we have that z-score of 2.83, we can visualize our normal curve here. 2.83 is going to be somewhere up there. Now thinking about the type of tail test, we could picture it in two ways. We know our alternate hypothesis is using some sort of greater than symbol. So I'd be looking for the area that's bigger than that z-score of 2.83, or in other words, to the right of that z-score. Another way to interpret it is this is the area of the normal curve that would support the null hypothesis, being 30 or less. So what we need to do is we need to find the area of the red, so it's a right-tailed test. So what we're going to do is just we're going to use our normal CDF function. So on my calculator here, I'm thinking about using the normal CDF, or you could use a standard z-table as well. I'm using the calculator because it's a little bit faster for me. So normal CDF, we are going to start counting our area at 2.83, and we're going to go all the way to the right, which is infinity, and remember infinity can be replaced with 1 times 10 to the 99th if your calculator does not accept infinity. Describing the curve, this is a standard normal, so our mean is 0 and our standard deviation is 1. And what we get for that area is rounded approximately 0.0023. So that value there is our p-value. So our p-value is approximately 0.0023. Now for the final part of our hypothesis test itself, we actually need to compare our p-value with our level of significance. So we just calculated our p-value to be 0.0023, and we're going to compare that to our level of significance, which we set to be 0.01. Just to make it a little more clear on how we're comparing decimals here, I like to have the same number of decimal values after the decimal point, if that helps you see something. In other words, we can see that 100 of something is bigger than 23 of something, so we would accurately use this symbol. So in other words, our p-value is less than our level of significance, so because of this, we are going to reject H null. Now of course, if we're rejecting H null, that is actually supporting the claim, because our claim was the alternate hypothesis. So what we can summarize here we'd be able to conclude that at the 1% significance level, or using a 1% level of significance, there is enough evidence to support the claim that the mean raw score for the school's applicants is more than 30. And the big important note here is that we're supporting the claim. We're not actually proving it to be true. If we wanted to prove it to be true, we'd actually have to go look at the entire population, which obviously is not going to be worthwhile. So we're supporting the claim. For rejecting H null, we are supporting the alternate hypothesis. So our next example states that a manufacturer of sprinkler systems is claiming that the average activating temperature is at least 135 degrees Fahrenheit. So we want to test that claim. So to do so, we randomly select 32 systems and find their mean activation temperature, and then we also calculate their standard deviation. So we're wondering, at a 10% significance level, do we have enough evidence to reject the manufacturer's claim? So first we should state our null and alternate hypotheses. And in this case, our claim is actually going to be the null hypothesis because they say that it's at least 135 degrees Fahrenheit. So at least has a measure of equality in it. So that has to be our null hypothesis. So we're going to say for our null hypothesis that the mu value, the average activation temperature, is at least 135. So 135 or bigger. And then this actually is the claim, just so we know that if we reject the null hypothesis, we are rejecting the claim, which is going to make, by default, our alternate hypothesis the complement to that. So if you're at least 135, the complement to that would be in less than 135. Now, just keeping track of the information we have, we can see that the hypothesized average focuses around 135 degrees Fahrenheit. Our sample mean was 133 degrees Fahrenheit, and the standard deviation of our sample was 3.3, and then our sample size was 32. So the first thing we need to do is calculate our test statistic. We need that z-score so we can find some area. So we're going to calculate our z-score for this, and of course it's the sample average subtracted the hypothesized value over our standard deviation divided by the root of the sample. So our sample average was 133. We're going to subtract the hypothesized average of 135, and we will divide that by our deviation of 3.3 over the square root of our sample size. And when we do that, we get a z value of negative 3.43. So we are going to use that z value, negative 3.43, to help us calculate the area for our p-value. So we're drawing a standard normal curve, and we're imagining what type of tailed test this is. First, I'm going to place my z-score of negative 3.43, which is a large amount of standard deviations away from the average at 0. So I know it's going to be somewhere over here as a crude picture. So this is z equals negative 3.43. So I know the area to the left of that should be really, really, really small. Now, if we're thinking about the type of tailed test that we want, there's two ways we can think about it. Since our alternate hypothesis is using a less than symbol, that forces it to be a left-tailed test when we're focusing on our level of significance with alpha. So we do know it's a left-tailed test. Another way we've discussed in class is thinking about what area is supporting the null hypothesis. And the null hypothesis is stating that the mean is bigger than something. So this area, if we had sample averages falling in there, that would actually support the null hypothesis. So either way, we can see that we're going to be running a left-tailed test. So we're looking for the area that's left of the z-score of negative 3.43. So again, we could use our standard normal table. I am going to be using my calculator's normal CDF function. So for that, we want to start counting area all the way to the left. So all the way to the left is negative infinity. And of course, remember, if your calculator doesn't accept negative infinity, we're going to type in negative 1 times 10 to the 99th. So the biggest negative number that our calculator can handle. We want to stop counting at our z-value of negative 3.43, and then just describing our normal curve has a mean of 0 and a standard deviation of 1, as always. So when we calculate this, we get an approximate area to the left of that z-score being 0.0003. So that's our area. So to finish our hypothesis test, we just need to compare our p-value to our level of significance. So we just calculated our p-value to be 0.0003, and then our level of significance, just by definition, was 0.10. Now this one's very clear to see that the level of significance is bigger than our p-value. So because of that, we are going to reject H null. So we can summarize with a quick little statement here, which I'm going to pre-prepare for us. What we would say is at a 10% level of significance, there is enough evidence to reject the claim that the average activating temperature is at least 135 degrees Fahrenheit, just because our claim was actually our null hypothesis and we were rejecting that.